Well, welcome to the second video from chapter 2. In this video we're going to deal with sections 4.2 and 4.3. Essentially we're going to look at the concept of linear correlation, sometimes called linear association, but almost always linear correlation. So imagine we have a scatter plot and the data is some kind of straight line, and we would expect in that situation then to have what we would call a linear correlation. So when you've got this straight line, what's the kind of things that you are going to work on? Well, one of the things you're going to work on is that what would be the equation of that line. So you can imagine in 2 dimensions you've got a set of data that is linear and you're trying to draw a line through it. And what is the best line that you can have? If you look at textbook, there's a number of different names that they give to this, the best fitting straight line through a set of points. It can be called the best fitting line, the line of best fit, a least squared line, but the name linear regression line is the best one. Now when you draw a line through a set of data points, if you look at each separate data point, with a few exceptions, they're not going to be on the line, they're going to be a little bit off. Some points are going to be a little bit above the line, some are going to be a little bit below the line. And we call the difference between the y value of the line and the y value of the data point, we call these the residuals. And you'll see that what you would get for the best fitting line would be the one that would have the fewest number, total number of residuals. And there's a calculation, it's quite a messy calculation, where you can actually find that the line of best fit, the regression line, is unique. In other words, for any given set of data points, you're going to get one line that's better fit than any of the others. And if you wondered how they come across it, how they create it, I want you to imagine this is our data set. And this line here represents one of the possible lines that could go through the set of data. Now you can imagine I could drop the line a little bit lower, I could make it a little bit steeper, I could move it around in a multitude of ways. But let's pretend for a moment that this is the one that we're dealing with. Then for every single one of these points, if you calculated the vertical distance that it is away from the line, all these things called residuals, you can't just add them up, unfortunately, because some of these numbers are going to be positive because the data is above it, and some are going to be negative so the data is below it. And if you just said, well, I'll add up all the pluses, add all up the negatives, combine them together, you could end up with, theoretically, an answer that's 0, and none of the ones work. You imagine a point that was here, and then the next one was the same distance but below it. Third point was up here, the fourth one was lower. They could eventually cancel each other out. So what they in fact do is they take all the residuals and they square them and they add them up and they try and find which line would generate the smallest total to the squares of the residuals. So that's a theory about how that particular best fitting straight line comes about. So let's imagine that we've got some data and we want to find this line, the best fitting line, and we'll call it y equals a plus bx. So a bit like algebra, but you tend to put the constant first and then the multiple of x second. And this is one of the ways in which you can calculate it. A and b. A is essentially the y-intercept, and b is going to be the coefficient of x. Well, the coefficient of x, the b value, can be found by what's called the correlation coefficient r, multiplied by this fraction, and a can be found by this fella here. So can you imagine you've got some data points and you calculated the standard deviation of all the y's, you divided it by the standard deviation of the x's, you multiplied it by this number called the correlation coefficient, and the whole thing gives you b, and then the mean of all the y coordinates, take away b times the mean of all the x coordinates, that gets you a. So you really can imagine how number intensive that would be. The good news is that for the most part you're not really going to calculate these by hand, and for the few times that you do calculate it, I have a video out that shows you how you can get your TI-84 to do it for you, so it's really not too onerous at all. What we're more interested in is looking at linear regression lines and seeing what we can do with them, and also to look at regression lines and deciding whether or not they give good results, good predictions. So imagine in this situation from this one below, the X is the protein content and Y is the fat content. So they looked at various hamburgers and they got the protein against the fat, and maybe that's McDonald's big one and that's whatever Burgers R Us, and so lots of different places, lots of different companies. But the data is linear. One calculated for us, the A was 6.8 and the B was 0.97. Then we, instead of saying Y equals 6.8 plus 0.97x, we say, instead of the Y, the predicted fat level, and instead of the X, the protein. So you don't normally write equations down in the algebraic way, Y equals 2 plus 5x. You write it down as predicted, whatever the Y is equal to 6 plus 2 times whatever the X variable is representing. So if you have a formula like that, then you can use it to make predictions. For instance, if you had a burger with 25 grams, or whatever this is, spicy chicken thing, 25 grams of protein, you plug it in here, you do the calculation, and this is your predicted answer for how much fat it's got. Now, it's not a perfect world. It doesn't mean I guarantee that this particular chicken burger or sandwich will have exactly 31.1 grams. What it's saying is our model's best predicted value for it, based on the evidence that we have, the data that we've collected, is somewhere in the region of 31.1. We would hope that if it was a good tight model and the data points didn't vary too much, that the right answer would be darn close to this most of the time, and that's probably the best you can ever hope. Suppose someone actually found for that particular one what the exact value was. So they got the thing and they calculated at 35 grams of fat on it. Then we can calculate the residual to see how good our predictor was. Well, if you take the observed value and you subtract the predicted, it's about 3.9. So 3.9 is a residual. And if you look at it's probably not a great answer, but at least it's not miles off. It's not like half the right answer. Now, when you have a correlation coefficient, which you always do, these fellas represent something quite important. It represents how good a fit the data is to that straight line. So the correlation coefficient always ends up between 0 and 1. 1 would be a perfect straight positive line, and at the other side, instead of 0, you should say negative 1, and that would be a perfect fitting line that's got a negative slope to it. And right in the middle is r equals 0, and r equals 0 would represent virtually nothing of use. It's just total random data. There is no connection between the x and the y. A lot of the time we don't use the r value, but we square it and we get this fella here, 0.69, which is converted to a percentage. And r squared is called the coefficient of determination. So in this case, 69% is kind of middle of the road. You really would like r squared, the coefficient of determination, you really like it to be like 80s and 90%. The jargon for what this is saying is that our particular straight line, 69% of the variation that you observe is predicted by the model. So 100% would mean you had a perfect straight line. There is no variation, it's 100% right. And if it was like a 5%, you could probably quite safely say that the straight line is useless as a model. You might as well just guess and you would just as you're just as likely to get near the correct answer as the models predicted it. So here is a worked example. This, in fact, is online. You can read through it as a PDF. But we have an equation here, and what they've collected data is that children between 5 and 15, and they've measured their height. And so at the end of the calculation, the predicted height of a child is 15 plus 3 times their age. So if I know the age of a child and I plug it into this formula, allegedly it would give me a good prediction of the height. Now, since the correlation coefficient R is 0.75, it tells us that the line is positive, which is not a surprise. The older you are, the taller you are, so yeah, that would be positive. I'm not that impressed by the coefficient of determination. It's 56.25%. Yeah, there's a lot of variation that's not accounted for by this model, which tends to mean that we could be, in some circumstances anyway, we could be miles out. Now you can actually interpret the equation as well, the 15 plus 3. The y-intercept, the 15, is typically the predicted age at 0, right, the y-intercept. In this case you could say 15 inches would be the predicted height of a baby. Now the 3, the coefficient of x, what that's saying is that for every time x increases by 1, so in this case for every year older you get, the model is predicting that you would grow another 3 inches. Now you can imagine if you've got children that doesn't work. They shoot up, or it's 4 inches or it's 2.5 inches. But this is a predicted height for everybody, so that's why we've only got a 56% coefficient of determination. I'm pretty sure that there's a lot of variation that can happen within this. Now, if you look at one of the questions was asking what would be the predicted height of a 12-year-old, well, if you plug it into this formula, you get 51. You can calculate the residual. And then we have a weird question. If you try to use this model to predict the height of a 6-year-old, which you shouldn't, because the data that we have here was only children, right, 5 to 15. You should never use any correlation model, any linear correlation, outside the range of its data, because you're asking for trouble. And let's see what kind of trouble we've got. Well, if you plug in 60, you end up, according to this model, that the predicted height is wrong. Obviously, 195 inches is not the typical height of any 60-year-old. In fact, any 60-year-old. And what's going wrong there is that the linear model is good if you're 5 to 15, and it might work 16, 17, 18, maybe up to 20. But we all know that for almost every human being, you stop growing at a certain point in your life. And so what the data would be predicting is that it kept on increasing, or at least the model's predicting, that it was increasing throughout all those years, which it certainly wasn't. So the moral of this story is, and the jargon term that's used here, is extrapolation. That's when you try and plug numbers into your formula, your model, that are beyond the range of where the data was collected. So if you collect data on 20, 40-year-old males, right, 20 to 40-year-old males, don't use the formula to predict what a 10-year-old kid would be like, or what a 90-year-old man would be like. That's extrapolation, not a good idea. Here's another one about the doctor collected data on some deceased patients, and he plotted the number of cigarettes that they smoked per week. I'm assuming that when he interviewed them when they were alive, he asked them that. And he computed, correlated it against when they died. And in this case, the y-axis is the predicted life expectancy, and it ends up being 77.4 take away 0.37 times the number of cigarettes. So we're going through the same process as we did the last time. It's a negative R value, which means it's decreasing, which is telling us that when you smoke cigarettes, your life expectancy goes down. The 77.4 is what you would expect the life expectancy to be if you'd smoked 0 cigarettes. So that represents that number there, the life expectancy of a non-smoker. And now if you say, what about this fella, the negative 0.37? You could phrase it something like this. For every extra cigarette per week that you smoke, you will take about 0.37 years of your life expectancy. You've probably heard or seen stories that say things like, for every 5 cigarettes that you smoke per week, you decrease your life expectancy by 4 years or something. You're wondering where that's coming from. It's coming from this stuff here. Now, they've got some predicted ones here, and then you can make a conclusion that the more you smoke, the shorter your lifespan's going to be. And there's some other examples here, but let's move on to how do you test the data. So what we're looking at here is, suppose you've got a model. You shouldn't just blindly use a straight line through it and do linear correlation and then come up with predictions. If you can tell before you even started that your model's not up to the job, in other words, the data isn't that linear, if even vaguely linear, and you're trying to pretend that it is, you're just going to get garbage in, garbage out. I believe it's a computer term. So I'm scrolling through some other examples while we're doing this. And here we go. So what you do if you want to test how good your model is, and computer software really does this for you, but we'll show you the theory behind it. There's your straight line, there's your residual. On this diagram to the right, it's a residual plot. A residual plot is what the x value is, and instead of the y being the predicted fat, the y value is the residual that you got. So at this one here, if the residual was -3, over here you'd plot the point and it would have a -3 there. So how does this residual plot give me some information about how good or bad it is to being linear? You're never going to get a whole set of dots all along 0, because that would be the data was a straight line and all the points were on that straight line. What you get are guys above and guys below. If you see a kind of band where they jump up and down with no rhyme or reason, then you're pretty safe that your data is probably quite linear. What you've got to be on the lookout for, and so that's actually a good residual plot. You don't want these numbers to be huge, of course, because what that means is that it's linear, right? The data is linear, it's a straight line, but it's not very concise there, right? It's got a lot of, it's not consistent, it's got a lot of bad variation in it. Now here's 2 examples of what you don't want to see. What I see here is a whole load of ups and a whole load of downs, like a happy face. That's a bad sign. It means your data's not linear. What I see here is starts high and then gets low. That again is a bad sign. That is pretty much telling us that our data is not a straight line. So if you were doing this and you were trying to collect data, maybe medical data and so on, and you were assuming that the model was linear, you would get the software to plot these residual plots, and as long as you see this kind of band of nothing very interesting happening, you could be comfortable that your linear model's a pretty good fit. If you see any kind of shape in it, then linear is not your model. We only do linear, but theoretically there are quadratic regression, logarithmic, exponential regression. There are lots of other regressions, and what they basically do is they take your data set and then trying to fit the best straight line through it. They try and fit the best log function through it, or the best exponential or quadratic, and that hopefully would give you much better predicting qualities from your model. And that is the end. Thank you for listening.